Okay, so this is our week 4 discussion. And this is example number, I guess you can call it 2 or page 2, whatever you want to call it. So in this one, we're going to start putting everything together. I have a rigid member A, B, D, E. A, B, D, E. And it's important that it's rigid because that means it's rotation. We don't assume any deformation taking place in here. As we push on this, the whole thing is wanting to rotate about A and not just rotate at D. It's a rigid, it's like my pencil. It's rigid. It's rigid body rotation. It's supported by a single shear pin connection at A and at B with a tie rod. The tie rod is attached at B and C with a double shear pin connection. The pins A, B, C have an ultimate shear strength of 80. The tie rod has a yield strength of 60. We have a concentrated load of 24 kips. It's applied perpendicular to DE, and we're going to use a factor of safety of 2. So again, if you haven't watched the lecture videos, you might want to make a point to go back and watch the lecture videos because that's where I actually go into depth about what a factor of safety is. But essentially a factor of safety is we kind of know what the ultimate stress or the failing stress or the yielding stress of the material is, and we say we aren't comfortable designing to that limit, so let's reduce it. Let's use a factor of safety, and we're going to reduce our strength. Okay? So there's a lot going on here. So as I push on this, it's going to want to rotate it. And I can see it's going to want to rotate it about this pin here, and it's going to put this tie rod, which is a 2-force member, which is super important because that means the X and Y components follow the same geometry as the tie rod, but it's going to want to put that in tension. So as I'm looking at this, as I push on this, it's going to want to cause rotation. So we have this tie rod in here, and if you look at the tie rod, we're going to get super fancy. If we see it's a tension member, as it's rotating, it's going to want to stretch, right? As this thing is rotating around, as we rotate from here and around, it's going to want to stretch. So I can see that's a tension member. And if it's in tension, it's got to have normal stress. And normal stress is that tension force over area, which we've been calling a normal force, because when I look at that tie rod, that force is going straight through the centroid. If I were to cut it, I could try to put internal shears and moments and torques, but the only force I have is normal. So normal, okay? And we have a pin. So a pin is going to be in shear. So it's what's connecting this A down here to this piece of wood. And so, it might have a piece that comes up like this with a hole bolted through it. And then I've got that member right here, and then I'm going to bolt them together. Okay, bolt them together. So as I'm pulling on this, that shear bolt, that bolt that's coming through is going to want to shear in half. It's like cutting a loaf of bread. And when I cut that loaf of bread, that force is shear. So our pins are going to be shear because that force is parallel. And our tie rod is going to be normal because the force is perpendicular. Okay. So we want to determine diameters. So if I know that normal stress is N over A and shear stress is V over A, that's all the formulas we have so far. That's it. And I'm told that we have an allowable strength of, okay, well, Professor Emerson, I don't know what the word strength means. Is that like a force in pounds, or like what is it? What are my units? My units are going to tell me that is a stress. It is in units of kips per square inch. So I am given that the ultimate shear strength, my ultimate shear strength is 80 KSI. And the ultimate yield strength, okay, is 60 KSI. I know that those are my given strengths, my given stresses, because it tells me in the units of KSI. It's not a force, it's a stress. Okay, follow the units, follow the units, follow the units. I also know that I want a factor of safety of 2, so I'm going to divide both of those by 2. So I'm going to end up that my normal stress that I'm allowed is 30 KSI, and the shear stress that is allowed is 40 KSI. Okay, so I've got the stress, that's done. Mark that off. I'm trying to find the area, so I should be able then, based on what I'm given, to find the normal and shear forces. So this is where we go back to our friend statics, and we draw a free body diagram, and we draw this rigid body, okay? And I'm going to go ahead and I can see that this has an X and Y component. And if we're rotated 20 degrees up, then we're rotated 20 degrees over. So sine is X, so I have 24 kips, sine 20, and I have 24 kips, cosine 20. Those are my X and Y components. At A, I have a pinned connection, so I have AY, and I have AX, and I have this tension member. So we can just call that the normal force in BC if we want to, because we know it's acting in normal. And now you say, holy cow, I can sum forces X, I can sum forces Y, I can sum moments. Okay? The magical thing about a two-force member, remember it's a force at this end and a force at this end, is that the internal normal force is going to follow the same geometry. So we are at 6 and 9 divided by 3. So we are at 2 and 3. I just divided it to make it smaller numbers. And the hypotenuse then is going to be square root of 13. Okay? So I know if you wanted to go back and look at the components, okay, if I wanted to go back and look at the components, that the X component of this is going to be 2 over 13, okay, times NBC. And I know that the Y component is going to be 3 over square root of 13 NBC. And so we've now gone from, you know, what is this? What's the moment arm? I don't know what's going on, to the X and Y components. And it is, both are a function of NBC. So I have unknown normal, unknown AX, unknown AY. And I have three equations of equilibrium. So let's start with summing the moments about point A. Okay, we can sum the moments about point A, then we get rid of those unknowns. I'm going to cover them up. I'm going to walk my way up. Okay, well, the Y component, because it's on this bracket, is going to come straight down. Okay, you can see it's at the centroid. It's going to come straight down. It doesn't cause a moment, but I am going to have this X component. So I have negative 2 over square root of 13 NBC. Okay, and its distance is 9 feet, and then 4 feet, 9 feet up. Okay, now I have the X and Y components here. But now you're like, well, I don't know what this X and Y distances are. I know that this 24 kips cosine 20 is going to be coming straight down, but what is this X distance? And I know this 24 kips sine 20 is going to be here, so I'm going to be walking up 13. What is that Y distance? Well, I do know that this is 20 degrees, and I know that the hypotenuse is 8 feet. And if I know that, I can calculate my distances, because sine 20 equals Y over 8, okay? And cosine 20 equals X over 8, X over hypotenuse. So I actually now have distances for all of these, okay? So if I'm summing my moments about A, I have, why did I call that a negative? That's clearly a positive, right? Positive right-hand rule. Positive 2 over 13 NBC times 9. Now I have minus 24 sine 20. Okay, that's the X component. And its distance, its perpendicular distance up, is 9 plus 4 is 13 plus, okay, plus 8 sine 20. 8 sine 20. That's the Y component. Minus 24 cosine 20. That's the Y component. Okay, its distance is this X arm. So times 8 cosine 20. And all of that madness has to equal 0. All of this madness has to equal 0. 2 over square root of 13 NBC times 9 feet minus 24 sine 20. Its distance up is 9 plus 4 is 13 plus 8 sine 20 minus the y component of that applied, so 24 cosine 20, okay, times its perpendicular distance, okay, is the x component of that triangle, so it's going to be 8 cosine 20. And when I work this out, I get that the normal force in BC equals 59.83 kips. Okay, 59.83 kips, which is awesome. So now I can go back and I can sum forces in the x direction. And I have AX minus 2 over square root of 13 times 59.83, okay, plus 24 sine 20 equals 0, and AX equals 24.98 kips to the right. And I can sum forces in the y direction, and I have AY minus 3 over the square root of 13 times 59.83 minus 24 cosine 20 equals 0. So AY does indeed equal 72.33 kips up. So I'm going to come back up here, and AY is 72.33 kips, and AX is 24.98 kips, okay? So we're going to start with the tie rod. We're going to start with our only component that's normal force, okay? And our normal is sigma. It's the normal over A. For the tie rod, I already found that my allowable stress is 30 KSI equals, well, the normal force in my system is the normal force that I got from statics, 59.83 kips, divided by, and it tells me that I need a diameter. So it needs a diameter, so I know it's circular. So I'm going to have pi over 4 diameter of CB squared. And when I work this out, the diameter of CB, okay, the diameter of that rod equals 1.59 inches. Look how easy peasy that was. Now let's deal with our shear. So our shear is tau, and it's V over A, and I have a pin at B, and I have a pin at C. And I already know that if this is pulling up in tension at 59.83, then our support is going to be pulling back down, equal and opposite, and they're connected by a pin that's going straight through there, a pin. And that pin, okay, that force is going to be acting shear because that pin is going through here. So if we could draw kind of a 3D-ish picture, there's the pin that's going through the system. There's my pin kind of in that direction. And I have a tie rod that's coming around that's pulling in this direction. And I have a support that's pulling back. And so we can see that we're going to end up with a shear force that's wanting to separate. Okay, we're not pulling the bolt apart this way, but it's literally this kind of a connection, right? It's this kind of a connection. It's like we have, here's a member, here's a member, here's the pin. So I'm pulling up in tension at 59.83. My support is pulling back at 59.83, and this bolt is holding it in place. So if we were to look at the shear plane of that bolt, that normal force has become a shear force, okay? So if I look at pins B and C, because it's a two-force member, it's going to have the same amount of force in there, so I know that I have a shear. So my shear is 59.83. My allowable shear was 40, so I have 40 KSI equals 59.83 kips. That's the shear force that's going to be acting across that bolt. And it's in double shear. It's a double shear pin. So it would be like if we did this and we had a little bracket at the base that was connecting it into the ground. And so I'm pulling at 59.83 with my tie rod, and I have this bracket top and bottom, the pin is going all the way through, so I actually have 2 areas that would have to be sliced for this plate to come out. Do you see that? For this to go away from the ground, it would have to slice through like 2 slices of bread, or I'd actually have to cut out a loaf of bread. So I have double the area. That's the beauty of a double shear connection, is that I have double the area. Pi over 4 times the diameter of B squared, or C because it's symmetric, and I get that the diameter of B, which equals the diameter of the pin at C, is 0.98 inches. And now I have to deal with my bolted A, and it was a single shear, so it's going to have 1 area. So I have 40 KSI. And, oh, I have to deal with this. So I have an X and a Y component that I found, an X and a Y. Do you think in the real world this is going to break magically into an X and Y component? Okay, it doesn't. Really, I have a magnitude that's going across that bolt of 24.92 squared plus 72.33 squared, because we don't magically break into this XY world. We actually have a shear force that's a magnitude. And when I find the magnitude of that shear force across A is 76.53 kips. Okay, so my shear is 76.53 kips. My area, single shear, so just pi over 4, diameter of A squared. And when I work this out, my diameter of A is 1.56 inches. So there we go. Now, if we had to round this to the nearest, say, 1/4 inch, because I can't go into Lowe's and be like, I want a 1.59 inch bolt, a 0.98 inch bolt, a 1.56, you can't do that. So if I had to round to a 1/4 inch, a 1/4 inch would be a 1 inch, 1 1/4, 1 1/2, 1.75, or 2. This is going to round up to a 2 inch. This is pretty easy to see, a 1 inch. What does this round to? Like, what is this? Oh, I was rounding to whole inches. Erase, erase, erase. We're going to go to 1/4. Okay, if it's 1.59 inches, and I can either be at 1.5 or 1.75, that's right in between. Do I round down to this because it's closer, or do I round up? Okay, you always round up on a bolt size, always, because this is the minimum diameter. This is the minimum diameter. So using this information with this load and this material property, the minimum it can be is 1.59. So if I have to do any rounding, I'm going to have to round up to the nearest 1/4 inch. I'm going to have to go up to 1.75. Okay, same with this. I can't round down to 1.5, even though like it seems like a closer number than going to 1.75. I'm going to have to round up to 1.75 because this is actually a minimum diameter. Okay, so I hope y'all are understanding that really it's the statics, and then it's understanding, is it a normal force or is it a shear force? We do have one more problem. It'll be in a different video, and it's going to be a whole lot shorter than this one. So this was the longest of them all.